Video is starting. I hope the live has started. What is the round name? Can I give the round name quick? 1055. I have 36 seconds to open the folder. I hope I can do that. VS Code is not working well. Maybe I'll share my screen because it's about to start. So I got a new. Also have a new water bottle. So we have 18 minutes. I hope it's private. I hope it's private. I cannot ruin a stream. I cannot ruin a contest. I hope I'll do good. Okay. N0, his goal is to transform the given array using minimum number of operations to a target array. You can perform the following two types of operations any number of times in any order. Increase, choose an element x, increase all elements, choose a positive integer, increase all elements of the array a by x. In other words, he chooses a positive integer x for each I he replaces. Okay, smash, get some elements, possibly none or all, to zero. In other words, for each I he replaces AI with 0 or leaves it as before. Okay, so we can choose a subset and squash them, or we can do that. So number of distinct elements, right? For each distinct, you have to increase them once, and then maybe you will squash other things. So maybe number of distinct elements. Find the number of total of minimum total number of operations. Uh, increase, smash, and then increase, smash, and then increase. Would that be enough? Number of distinct elements. Two times number of distinct elements minus one. I'll guess it. Two times number of distinct elements minus one. One, two, three. Because you have to guess, right? Yeah, I think that works because it's an easy problem. I have to be quick. Would that work all the time? Yeah, it works because initially they are zero and we don't have zero in the constraint. Probably. I hope I don't get stuck in B because last time I got stuck on B. Let me submit. If you don't let me submit, what I have to do? I have to go here and then I have to go to Codeforces and then I have to go here and then I have to select it and then I have to open it. By then this would have been active. Wait, am I wrong? I think it's because of in queue it has less solves. So don't give much importance to less number of solves and go to the next problem. B looks scary. Doran and the Krug are playing a game on a grid of n plus 1 cross n plus 1 cells whose coordinates are pairs of integers. I hope I don't have viewers. Yeah, I don't have viewers. Uh, Doran and the crew are playing a game on whose coordinates are pairs of integers. The goal is to not get caught by Doran as long as possible, while Doran's goal is to catch the Krug as early as possible. We say Doran caught the Krug if they stand in the same grid cell. To play the game, Krug and Doran take turns starting from the Krug. Krug can either stay in the same cell or move to a cell vertically or horizontally, but not diagonally adjacent. Formally, if Krug is currently either she can stay at or she can move to the Doran can either stay in the same cell or move to vertical or horizontal or diagonal adjacent cell. Okay, the other guy can go more. Both cannot go outside of grid. number of times Doran's crook several time is defined as number of times Doran's turns until Doran catches crook for the given. They can stay or move. Both of them can stay, same or move. Okay. We have n plus 1 cells numbered from 0 to n. So we have two people's coordinates, and then we have to just say crook survival time when both players play optimal. So what are lower bounds here? I know it's an overkill to call lower bounds on this problem, but why not? If both of them had same thing, he will try to move towards him. He tries to move opposite. So, but then he can come diagonally. He can do two things. He can do two things, or he can do one thing. He can do two things, or he can do one thing in his direction, right? So we have these two things. After one thing, till he reaches this corner or this corner, till he reaches this corner or this corner. Okay, if he's reaching this corner, how long would it take for this guy to go to that corner? In optimal, he will always reach some corner, right? He will always reach some corner. Okay, and then this guy also will reach that corner. Why? He can always make sure that 1 minute. No, he need not reach a corner, right? If he is here, the vertical distance, if both of them itself, let's say if the distance is 6, okay, 3 plus 3 is 6. He can only do 3 this side or this side, but this guy will reduce both of them minus 2, minus 2, minus 2. So he will catch him. It has some complexity. Let me read this one too. Let me see if I have passed that one. Yeah. Not too much complexity, little bit of complexity. Okay. But then I cannot mess this up. Let me solve this and then only go. Okay. So let's say 3 and 3 is the way. Then he can increase that Manhattan distance by 1. But then this guy will reduce the Manhattan, can reduce the Manhattan distance by 2. Right. If they are in the same line, only then he will reduce it by. Okay, if they are in the same line, okay, yeah. So if the distance one of them is more after this guy's operation, he will surely come closer. Right. So as long as both dx comma dy are greater than 0, dx plus dy reduces by 1. And then now we have this thing. Let's say he increases that. That's definitely not a better thing to do. Right? Let's say it matches, but then he can choose to either go to this corner or to go to that one. He can either choose to go to this side or to this side. Finally, the vertical thing, because even if it matches, he can try to choose to go towards this one. Okay, I see it. It's like once they come into same line, then once they are in same line, he can either go this side or he can go straight. Okay. If he's going straight, that would be the end. Even after going straight, he will try to move to one of the side, right? Okay, this has some cases at least. It's not that easy. Let me read C. It's not that easy. We have to be a bit more careful in some cases. Maybe I'll solve C instantly. So let me read C. If we're not wasting time, I can definitely solve B because I can see a few things. If we are here and if you are here, if you're in the same line, you can keep going like that and the other guy can't do anything. He has to follow you. And once you go there, and once you touches there, then you will start going this side. Then he will come and catch you. And then it will be bounded by the corners. So how can I do that? Wait a minute. The other guy can always reduce the bigger thing. He will reduce both. So there can be some guess that can let me solve it quicker, but then I'll go to C. Tired of supporting ranged carries. Carrier is now creating a data structure problem about range queries. For a problem b of length and b equals 0 or 1, consider the following triple removal operation. Choose indices I, j as the elements the positions are identical. Remove these three elements from the array. The cost of this operation is defined as minimum of k minus j comma j minus I. After the removal, the remaining parts of the array are concatenated and the indices are relabeled. So minimum of k minus j comma j minus I. Okay? You want to make the array be empty using the triple removal operation. Hence, we define the total cost of an array as the minimum. Okay, this is a good problem. Sum of triple cost removals required to make the array empty. If it's impossible to make the array empty, cost is defined as minus one. Carrier wants to test his data structure. For this, you must output Q independent queries. Initially, you are given an array. So this should be some simple thing. It has only 0 and 1s. Okay, that's something else of length and where AI equals to 0 or AI equals to 1. For each query, you are given a range. Okay, so we have to work on what is cost. This is a better problem. Not, I mean, B is also good. What is cost? Number of zeros must be 3 multiple. Number of ones must be 3 multiple. And now what's the answer? We have to be very careful here. Now what's the answer? Okay, can we always make sure that can we always do operations of cost 1? We can, unless it is 10101010. Unless this, you can always do that, right? Because you will have two things that are adjacent. Okay, let's only think of three multiples. If you only think of three multiples, unless these strings, you cannot do that. Okay, if we are thinking of three multiples. Now if this is the case, what can we do? Okay, 1 minute. Can we always do operations of cost 1? Okay, let me see if this is minus 1, right? When is it minus 1? 6 comma 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Here two, here there are not three multiples, so it is 0. Okay, when there are three multiples, unless this we can always do cost of 1. So cost must be at least 1, right? For one of for removing three things. So that seems correct so far, optimal. Here what can we do? Here we cannot use 3, but then can we remove this one, this 0, this one, and then this one, this one, and then this one, so that we will have 0 0 1 0 1 0 1 0 0. I'll remove this one and then these two things. So now what happened? Now we have two zeros. So then what will we do? We will remove one zero that is in between, and then we will remove these two things, so that we will always have 1 1 0 1 0 0. Okay. So can we do this all the time? If it's not 1 0 1 0 1 0 1 0, here we have to do one. I increase my brightness so you guys can see me better. 1 2 and remaining ones are enough. If this is not the case, can we always do that? Can we always do that? Let's say whatever is being remained is 1 0 1 0 1. At least this much will be remained, right? So what are we removing? When you're removing, you're either removing two adjacent ones, right? Okay, you're removing two adjacent ones. So you're removing two adjacent ones. And then when you're removing two adjacent ones, and some other one, can you always make sure that there will be two zeros after that? So except this, in every other case, can you always make sure that? How do you prove that? Except this case, in all other cases, can you always make sure that you will make sure that there is an adjacent one? How can you do that? Let's say you're removing ones. And after this, at least this much will be left out. So instead of those three ones, you choose this one. Okay. And now, whatever the remaining ones that are in between these two, you will choose them too. Okay. If the other ones are somewhere else, you will choose them too. So if you remove this one and the remaining few things, if they are not in between here, if you're removing three things, right? Okay. If those three things are here, only then you cannot remove. If they are not here, you can remove those things. But if four of them are here, you will remove this one and then these two things, so that it becomes 1 0 1 1 0 0. And then you can choose. Yeah, you can always do that. You can always do, unless it is all alternating. Its answer equals to len by 6, len by 3. Else it is len by 3 plus 1. Okay, because we will do one operation that is of size 2. So this is an easy problem. I hope it is right. I hope I have proved it correct, right? Why? uh, I mean, before this, if there were less than or equals to three things in this case, then what I will do is, instead of removing instead of removing I will try to remove these three, or whatever is here, and the remaining one that's coming from somewhere else. Then 0 0 will be formed for sure. But if all of them are here, you cannot make that argument. But when you cannot make that argument, I can make some other argument that I can remove some other one, because three multiples, right? At least we have many. So this is correct. I'll just maintain last alternate one. I need count of zeros and count of ones too, right? I need count of zeros and count of ones too. So I have to maintain prefix arrays. P0 of n, P1 of n. Okay. I'll make it like length alternate, last alternate, last alternate, last alternate. So last alternate from here, if that is less than L. But do we have that case here? Do we have such a test case here for 1 comma 12? Now 2 now. Okay, sorry. I'll test it like that. Okay, here it is. 6 to 11. 6, 7, 8, 9, 10. How? Not 6 to 11, sorry, 5 to 10. Why is it wrong answer? It had 500 solves, right? I should be careful. B had many solves. I should be careful. I hope problems are more difficult. Fuck. Two wrong answers. Why am I making these mistakes? I think my mind is not here. I'm somehow making weird mistakes. Okay, now what about B? Can I guess B? Is it whatever the maximum? Is it whatever the maximum? Is it like maximum of? Sometimes, even though you're here, trying to move this side would be better. Sometimes trying to go this side would be better. Right? So if he cannot catch you, then you can go that side, then this would be better. So this maximum is done. This maximum or this maximum, we have to think if you can go or not. Okay. I'll flip the board. Okay. So now we have this guy here and this guy here. So now, maximum of these two is definitely an answer. Now, can he go this side? Can he go this side? Or two questions. Can he go down? Can he go down? Is one question. When can he go down? One minute. It's going down. This guy can reach in between. This guy can reach in between. Then this guy is quicker, so you're coming down. You're coming down. He's also approaching you. Then you can you will always before you reach, if you are able to cross him, can you escape like that? Is what I want to try and think. Can you escape downward? If he is here, can you escape downward? How much can you escape if you can escape? You're going down. He's also going down, but he's approaching you, and then that will be at max this much. So I think this is the answer. We cannot do better than this. Okay, now we are here, and he's here. This is long, let's say. Okay, what is this case exactly? Column is same, but row is 64 and 63. This is the case. Rows are 4, columns are 1 and 2. Okay. It should be 1, right? I don't think there is infinite tens. Okay, is it minimum of them then? It's not that easy. Will this work? What's my logic here? If they both are equal, then you cannot do that. For the same reason you cannot go down. For the same reason you cannot make the opposite one. If the both are if the rows are not equal, then you can do column. If the columns are not equal, then you can do 1 minute. If the rows are not equal, you can do rows. If the columns are not equal, you can do columns. That's it. Will this work? Please, B, don't fuck me up. Because problems are not that easy. B is definitely not easy. Like, how can I prove this shit? Difficult, right? Hope it passes, and then I can do D, E, F, and everything. It passed, guys. It passed. We are here, D, E. I hope I can solve any of them. Let's see now, D and E. We can think coolly now, chill. Like, what can be the complexity of this problem? For an array B of length M, okay, consider the following two-player game. Two-player game. So games are good because we can work something games. Consider the following two-player game played by Poby and Reckless. The players must take turns with Poby moving first. On Poby's turn, he must choose an element X and replace it with X by 2. In other words, he picks I such that Bi greater than or equals to 2 and one bit will be removed. That's it, right? Yeah. On next turn, he must choose an element x greater than or equals to 2. What does greater than or equals to 2 means? At least 2 bits are there, right? Greater than or equals to 2 means 1 has only 1 bit, 0 has only 1 bit. There are two bits, you will remove one bit and replace it with x plus 1. And replace it with x plus 1. In other words, he picks I such that bi greater than or equals to 2 and does this. Okay. What this guy does is bi plus 1. The game ends once all elements in the array b are equals to 1. Yeah, if you keep removing bits, everything will become 1, right? Leading bit will come here. Define the score of the game as the number of moves that Poby makes. Poby's goal is to minimize the score, while Reckel's goal is to maximize the score. Okay, seems complex. Why is it complex? Because n is bigger. Okay, what if n equals to 1? Uh, you're given an array of length and answer q independent queries. So it's a very easy game because we have to answer q independent queries. Must find the value of the array. So it's an easy game. Because it's an easy game, what if n equals to 1? Think. Why is it an easy game? Because there are queries, right? There are queries. So that's why it's an easy game. So now we have n equals to 1. What should we do with n equals to 1? In your move, okay, you remove one bit per operation. But what what does plus 1 do to the number of bits? Only if all of them are ones, only here plus 1 will increase number of bits, right? Only here plus 1 will increase number of bits. So he can always choose something smaller like this and increase number of bits. He must do that. Okay, if it is just 1011001001, it never matters. One bit gone, other bit gone, other bit gone. Okay, we have this 0. So as you keep removing bits, at some time you come here. At some time this will be the value 11101111. So when this was the value, then what happens? After you remove it came become, when you do plus 1, it will become 1111. So it becomes this thing. And then what happens? And then what happens? When you do plus 1, it becomes 100000. You can only increase one bit per per index. Okay, why? Because all of them are zeros. So whatever happens, it becomes 1 directly. You adding ones will not help. You add 1, the guy can remove this thing immediately. Okay. So when n equals to 1, you have to solve well. Okay, guys, you should not get scared of d. First solve it for n equals to 1. For n equals to 1, answer is 11101111. Answer is number of bits plus 1. Because in this case, it's number of bits. This was not the case. Okay, this was not the case. This was not the case. Sorry, I doubt. I think even in this case, you remove that, add one, remove that, add one. Even if this is the case, you keep removing, the other guy keep adding ones, and once he adds ones, it will become 11000, and then you remove the bit, the other guy add ones, remove the bit, the other guy add ones, and then you come here, 1 1. You remove this bit, the other guy makes it 1. So even in this it's possible. But if it was 1011111, now whatever you do, it comes where 100, maybe it becomes like that. Okay, at some time it becomes like that after someone adds one. Now you remove 000. Once you remove this 0, he adds a 1 to that. So then it becomes this. So yeah, if there is a 1, if there is a 1, okay, only this is number of bits. Only this. Why? You are going to start and then you will remove that one. But if there was one somewhere here, that guy will protect this one always. He will protect this one. Whenever that one comes, he will protect it by adding plus one, and that one goes here. If this thing exists, it's this. Okay, so now we have two types of things. Okay, now we have two types of operations. If n equals to 1, if n equals to 1, this cannot be protected. So we have two things. We have two types, three types, let's say, all zeros, and then yeah. So these things are good. Whatever the other guy does, whatever the other guy does, you can remove. These things are always good. Whatever the other guy does, you can remove that. These things are always good. Okay, what about these things? These things are always bad. Are they always bad? Why? Whenever you remove here, the other guy will act on saving that one. These things can always be bad. Okay? But these things, they fight for. So is it simple problem? Or am I too good? Number of these things they will fight for. If you know number of these things, they will fight for these things. Okay. Alavis will try to remove this one. Bob will try to remove some, protect some other one. Okay. Yeah. And once they are done, let's say those things are done at Alice's step. From here onwards, the game is done. You don't have these anymore. Those things you operate or not, it's fine. These things you operate or not, the game is already decided. So it just depends on these things. So answer is number of bits plus number of good things by 2. Seal. Simple prefix sums will solve the problem. Because Alice goes first, right? Sorry, floor. Why? Number of bits plus number of fixed plus number of five things by 2. Because Alex will remove that, Bob will protect that. Alex will remove that, Bob will protect that. That's it. Number of 5 things by 2. Should I work on some case or should I just implement this? I think logic will not change much, so I'll just implement this. All of them has at least 2 bits. We have leading bit, we have this bit, right? Let's CBB. Let's array b of n plus 1 CBB that. What all I need? I need number of fixed things, number of 5 things, number of bits. Okay, I'll just add number of bits. If it's fixed, I will add it one more bit. So it's just number of bits plus number of fight. Count of fight, let's say. So I will find J. Most significant bit. I don't even need this. So we have this thing, right? So number of bits will be CB of I will be CB of I will be number of bits. Leaving this one, okay, leaving this number of bits, which is nothing but K. Sorry, J. Precisely J. And now what is this fight for things? Fight for things must satisfy X reminder true. You will fight it if it is odd, and you will fight it if all of them in between are 0, right? So let me say middle existing or not. Int mid exist equals to 1, 0. If middle exists, then mid exist, like in between there is something, equals to 1. Okay, mid exist equals to 1. So now if mid exist, if mid exist, then CB of I plus equals to mid exist. If it is existing, that's added already. That's a bit you can take it for granted, whatever the other guy does. But if that doesn't exist, people will fight for it, right? CF of I equals to X reminder 2 and should be odd and not mid exist. Now these things are what they fight for. But then I have to be careful. 1 minute. 10000. Whenever that guy touches them and adds one there, the other guy can remove that. Then all of them will be gone. I think it works. I'm thinking more. I think it works. It passed. Let me see source. Based on that, I can judge a bit. Fan handler. Fuck. Then it won't be more than this. How much time did I took? I think I took less than B. Right. The time I took on B. The time I took on B is 14 minutes. The time I took on this one is, let's make it 37, 20 minutes. Yeah, I took a bit more, but not too much. Let's try to solve E. This one was not that difficult. Probably E is also not that difficult, this means, right? Interactive problem. We have an interactive problem. Interactive problems are good. Faker is being naughty again. You asked him to create a nice query problem, but he created an interactive problem where he is answering a query instead. Faker hid a permutation from you, and you have to infer some information by interacting with him. You're given for a given integer, you're given an integer n. Faker hid a permutation of n square plus 1 length. This seems like either increasing length or okay. This is a theorem. There is a theorem. For more information about proof, I was trying to prove this one a lot of times. I even gave it to my people on my group to prove that theorem. Mm, our goal is to find a monotone sequence. I know this definitely exists. So we may want this proof. Erdos-Kerz's theorem. I was trying to prove these things. I was asking people to prove these things. Pigeonhole principle. Given a sequence of label ni, Nice proof. I was not able to prove this, but then it was nice proof, I guess. Yeah. So now to find you can make a at most n skyscraper queries to the interactor, which is defined as follows. You provide a k indices as a strictly increasing sequence. The interactor provides the hidden permutation at values. It's we have to use logic here. We have to use logic like this logic. What do we get? Interact items indices corresponding to visible skyscrapers from this set, and index ij is visible if its value. This may not be that difficult because it's an easy problem. Probably e is not that difficult. Is visible if pij is greater than values of all elements. So we can see p0. We can surely see pi. We can not see some things that are smaller. We can see the next one. We can see the next one. We can see the next one. We can see all these things. Okay. Don't talk too loud, don't walk too proud, and make it out as you go. So, what we can see, what we get, is not equivalent to longest increasing. Okay. Okay, this might be, we can use this. Okay, I think this theorem helps us, not pigeonhole principle. I think this theorem helps us here. Why? We want a chain of length or otherwise. Okay, this theorem, if you use this theorem, is done. It's helpful that I was thinking about this proof. I was trying to find the longest chain starting from here, remove that. Longest chain forming from here, remove that. Longest chain forming from here, remove that. Okay? And then you will have at most or minus one anti chains, right? Okay, when you take these things and then you write them, all of them. Okay, when you write like that, I don't think this works out to be very clear here. I have an idea. Remove from here, form a chain, remove that from here, form a chain, remove that. And is this what I thought itself? Can I prove that? Like, if the chain's length is n, you're done. If n plus 1. Otherwise, you have this one that came later. This one's end. After you remove these things, it came. Okay? After you remove those things, it came. I think it's done. It's done. It's done. Whatever I initially thought, that's enough. So whatever my initial idea was, that's it. I have tried to doing this proof long back. This is too simple problem. One minute. N queries, not n plus one queries. Okay, now if all of them are less than or equals to 1, then I can say there is some other index. So guess wise it's easy, but then I spent more time. Okay, why did I spend more time? I don't know idea why I spent more time. Don't want to brown, don't talk too loud. Wait, I haven't solved the problem. I haven't solved the problem. Fuck, did I fuck it up? Let's say I can have something like, this is all wrong, this is probably all wrong. If I can know longest chain starting at I. I take any chain, there is something greater than that that occurs before in the previous chain. Can I prove that? The first time It crosses that. First time it crosses that. Yeah. This is true. This is true. This proof is true. Okay, I wasted a lot of time. I should have guessed this question. It's very direct. That was very direct. I should have guessed that. Can I solve one of these things? One of these things. By luck. I could have solved it much quicker if I tried to guess it. So take whatever you are given. Let's read the problems right then. GS is analyzing a replay of the fight to understand his opponent's attack patterns. The opponent has a special ability. If they land three attacks on a target within a time frame of jet, then their attack. I thought of this proof long back. I thought of proving that long back. The opponent has special ability. If they land three attacks, which problem is easier among the next three? I will read all the three problems. Oh, the opponent has special ability. If they land three attacks on a target within a time frame jet, then time frame jet, their attack, the third attack becomes a powerful boosted attack. To outplay his opponent's use, should not let his opponent trigger their boosted attack. Y equals to be the multiset of m timestamps where y represents the time when the opponent's attack landed. We call to be safe if for every 3 timestamps it holds maximum of this minus minimum of this greater than z. For every 3 timestamps, maximum minus minimum holds greater than z. What does that mean? I don't get it exactly. Where okay, it has some sense. Any three must be far apart. So take minimum and maximum, they should be greater than z. And from minimum, the next thing that is greater than z, within z, you cannot have two things. Okay, you can only have one thing. And that's the condition. For everything, the next thing, for every value, the next thing within less than or equals to y plus z, there can only be one timestamp. So they are like far, far apart. Okay, okay, this problem is not that good, but then it's workable, right? It's workable. We have to work exactly what it means. Is z fixed? Okay, z is a fixed value. We have to work exactly what it means, right? So what it means for a set to be safe. Y0, y1 up to so on. Within y0, yi comma yi plus z, there can only be two things for each yi. If this is satisfied, then we are good, right? Because the minimum is there and you cannot have three things in there, right? If you're finding three things in there, that means it's contradicting this. If this happens, exactly if this happens, then it is safe. For the first one, if you're taking this, you can only take one more here. Okay? Is it taking the last thing always better? You take that, you take the next nearest thing, and then you cannot take till here, and then from here you can take. Okay? So if we do greedy, take x0, next thing. Now start from, is this the best one? X0 plus z plus 1 and proceed. Is this the best one? Is this the best one? How can I say this is the best one? x0 here, and then you have x1, x2, let's say, and then you have x3 here, let's say. So instead of taking these two, if you take these two first, then you cannot have anything from here. You cannot have the next thing will start from, let this be the first one. The next thing will start from here, right? So you must take first x0. There is a You can always take x0 because that's how greedy says, right? Okay, you cannot take from here, so you can just add that. 1 minute, you can just add that and replace. Can I always take x0, x1 is my question. Okay, whatever the first two things are, remove them and then add these two things. Now, if these two are going to contradict with the remaining, then the other things also will contradict, right? Probably. So I think this greedy works. Let's say this greedy works. Take first two and then go to x0 plus z plus 1 and then repeat from there. If this greedy works and if this is what you have to find quickly, how do you find that quickly? It is from here you start and then you go to the next one. And then you go to the next one, you go to the next one. Okay, but from here, but sometimes there may not be anything here. So it's just forming longest subsequence, let's say. Longest subsequence where adjacent things are greater than or equals to 1. How to solve this? And now we should count in this sequence if there is something else in between, you can take that too. So plus 1. So it's finding this thing. So let me come back to that. Let me read this problem too. This seems more difficult. I don't know. Maybe this is a bit direct one. I don't know. So we have to solve the problem. Wait, isn't it that's it? Isn't it like just maintain like something like sparse table and then you're done? Like 1 comma 6, let's say the answer is 3, it seems. So 1 comma 6, what I will do is I'll start from 1 and then all these things are there and then from 11. It seems that. Should I try to should I try to see if that passes samples the idea and then I'll just use patch table. Now I know one jump, from there another jump. So we have this greedy sequence starting at any value. So we do that greedy sequence and then we have a weight. If there is something else in between, there is additional weight. So from here, and then I have to correct the lost weight. So this is just an implementation problem, is it? So we have taken 15 and then we have to take 32. So after 32, ah, and second should come from, We have this greedy pair, and then second should come from x1. Is this still greedy? But is this still greedy? I don't have a solution. Greedy works, but then it's not that easy to implement that. Somehow. Why the previous things, second thing will influence this thing? Greedy works, but then, okay, let me just see if greedy works. I think greedy works, but then how do we implement this greedy? Is the question, right? But then we must do this greedy if it is correct. Greedy works, but then how do we solve this? Okay, let's say if greedy works, how do we get this structure somehow? For something starting from here, second thing is being affected, right? greedy works, but then how can we compute that? It's like there are two things, like it's like there are pairs. Maybe is it like some root n thing and root n thing? Let's not waste my time here. Let me read G2. Onit is a jungler, a role where you hunt monsters in a jungle. Given the number of trees he sees in a jungle, it's no surprise that he is addicted to the tree query problems. This should not be that difficult. This should not be too difficult. Like, okay, let's assume it's not that difficult. Then we have these pairs that keep going. And then what? We have these pairs. Can I say something about those pairs? Like, wait, it's just two chains. It's just two chains. We have this chain, and then you have this chain. That's it. Wait a minute. Is it just two chains? The fuck? Is it just two chains? Wait, it's just two chains. It's just two chains. But then the problem appears when sometimes this can be the case. The chain will intersect there. But from then what can we say? From then what can we say? We have two chains, but sometimes this chain may intersect to this one. From then what can we say? From here, I'll have the greedy answer. Okay, from here I will have the greedy answer. Okay, we have two chains. We have two chains. Okay. First time they may intersect. From there, it's a single chain. From there, I can have the answer, and we have to find where they intersect the first time, and then we will have a greedy answer from there. So we have two chains. We can try to find. We have two chains. We can try to find the first place where they intersect. From there, we can have the greedy answer. Then it's done. Then it's done. So it is not the difficult one. Can I implement this within time? Can I implement this? I have to be very clear with what I'm doing here. We have two chains, okay, and have the functionality of number of moves for each chain, and then we know after some number of moves the chains will merge, okay. Binary search to find that. Okay, if this was that index, now you have two chains, they may merge here. Now we have this whole structure, okay. Now, now you just want the length of these chains within this point. We have this point. If the point falls within, we have two chains. Sometimes they may merge. From then we have a chain. So from here, this we have this chain. We can subtract that once. We can add these two things twice. So I think if I can maintain that functionality, it's done. Number of moves. After these many moves, where will you be? After these many moves, where will you be? Okay. This is a direct problem only. I don't know why I thought of more of this problem, but then it's an implementation direct problem. Number of moves. Number of moves. Each time we move to some other point, right? Number of moves can be 28 max. In terms of two powers. Implementation is simple. I'll call it P. This is a very direct problem. I don't know why I have spent some time on this. Right? I don't know why I have spent some time on this. So take whatever you are given. And leave. After these many moves, you go here. You go to this index after these many moves, and then from there, these many moves you have to do. It's a simple problem. Now I have this functionality where I have an index and then I have some moves. Started I, started I. It's like binary exponentation now. After these many moves, where will you go? P of V of J is where you go. Okay. And then now you are here. You perform all the moves. So return V. It's patch table idea. Start at V, end at R. What would be your number of nodes? Okay, less than or equals to r. What would be the number of nodes less than or equals to r? After how many moves you will cross r? Or how many moves within r would be? Okay, these number of moves are within r. These number of moves are within r. So now we have e equals to l, u equals to l plus 1. Okay, let's see number of moves both can do until they are not equal. So if you do one more move, they will become equal. So these are the moves they can do until they are not equal, right? Let's say the common one be n z equals to p of v of 0. Do one more move, you will go here. Answer is fun of l comma, I don't even need do moves, plus fun of l plus 1 comma r minus fun of z comma r. So what does fun give? Let's say fun gives in this chain number of vertices. Okay, I'm getting scared. This is not a difficult problem, but then let's see if it passes, the idea passes or not. Do you have a smaller test case? I'll go to. Wait, there is more to the implementation. From here, you start from here, right? Okay, now there is more to the problem. But then let's just see if at least Z is being correct or not. There is something wrong. Can I find that within time? How to find it? So I have this simple test case where I'm doing something wrong. 1 and 4 should be the expected output. Then I'm doing something wrong. So 0, 1 comma 6, and then I'm telling for this the next thing will be this. So 1, 1, 1, 3, 3, 3. I'll first check if P of 0 is correct or not for everything. 0, 1, 2, 3, 4, 5. For this, it should have been 12. 0, 1, 2, 3, 4, 5. Yeah, it's correct. So let me run this test case. For this, 0, 1, 2, 3 should be the answer. For this, 3 should be the answer. For this, 3 should be the answer. For all these things, 6 should be the answer. Yeah, perfect. Now I'll run see if capital P of 0 is correct or not. For these two, they will intersect at 3 because both of them are going to 3. Is this the only error? It's not a difficult problem, but then it's weird because it's important. Okay, I have to be a bit more careful here. I have to be a bit more careful. I'm binary searching somewhere. I'm binary searching somewhere. I'm binary searching somewhere. Here I'm binary searching somewhere. If this and this, if both of them are less than or equal to true, only then I will come till here. Okay. Okay. Now if I analyze this, we are having v as 0. What is the answer for 3 and 6? You can take 7 and 8 and then you cannot take anything else. So answer should be 2. But then what's happening here? I'm getting V to be 5. 0, 1, 2, 3, 4, 5. How is that 5? Capital P, it should be capital P. How is V5? Capital P, capital P, capital P, capital P. Wait, is it capital P? Okay, no, this is small p. Hope that's the only error. I hope that's the only error. Please, it's an easy problem. It doesn't need any logic, but let me solve this problem. I want some rating. There's nothing logical in this. Like I don't even enjoy this. But let me get it accepted, please. Within 10 minutes, if something goes wrong, can I debug? Can I debug? I don't think anything goes wrong. It's perfect. Fuck. 1 minute. Fuck, fuck, fuck. This should be correct. Fuck, why is this happening to me every time? Why can't it be correct? Okay, I'm missing one case. Fuck, I'm only missing one case. When the next thing itself is greater than this. I should have handled this before. I should have handled this before. I think. I should have handled this before. If the match with zero moves, then what? I should have handled this before. Damn, Dominator has done so many problems. In their blogs. I was thinking about that. There are cases where I missed the case where this itself, like this and this intersect right here. I missed this case. I was thinking there are like two chains, and then they will intersect. 1 minute. Okay, this is two chains now. Okay, these are two chains. That's right. And then first thing that's greater than this. I thought these two are chains, but then this could have been going to this. That's the only thing I missed. Mhm. Both G and H1 got more solves, and Dominator was able to do very good even then. But very few people solved both, and he was one of them, I guess. 12th rank is 10. I can see something missing here. Should have been careful, I guess. I should have been careful, I guess, but fuck it now. It's an easy problem, but then there are some cases that I should have taken care of. Stupid implementations. Maybe I can just keep this itself, where this and this would intersect. Easy problems.